All right, sorry about that. The question was, when are the tests due? And I think all three people, let's see, I've got three people that are in all three classes. That would be Kira, James, and Jesus. Okay. Um, Ryan is only in this class, and Jemanuel is in both the calculus and this class, but he's not in linear algebra. Okay, so to answer the question, whoa, here's James. So let me get him in so he can hear the answer and not have to look for it elsewhere. So James is coming in. All right. We got every other student here, just missing Ryan and Jemanuel. Okay. James, the question was asked, when are the tests due? And it happens to be the three of you are the three that are in all three classes, and all three of you, I guess, got tests last week. Just happened to be you finished the material in about the same time. When are they due? Technically, I say a week, okay? But you can have more time if you want it, but I definitely want them turned back in before the next test. So just to give you an idea, in Calculus 3, we're now on 9.1, we're almost on 9.2, and we've just got three more sections after that, 10.2, 10.3, and 10.4. Then you'll have your next test on that one. Linear algebra, I can't remember which section we're in that one. Let's see, here is Ryan. Okay, let me get Ryan here, and now we're just missing Jemanuel. And I can't get my pen to operate properly. All right, so we're just missing Jemanuel. Okay. Ryan, the question was out there, when are the tests due? And for the three students who were here already, they have three tests from me. Happened to be, we finished material for the first test all last week in all three classes, just happenstance. Okay, for you it's just this one. And as I was saying, I'll pick up on this class in just a minute. The linear algebra class, I think, is going to probably be the next one we'll finish next, and then this one will be a little bit longer because this is a long chapter we're in now, and we got quite a bit to cover in this one. So I would say if you have to prioritize, Cal 3 would probably be top priority, linear algebra second priority, and this one would be third. But I would be doing as much as I can on all three of them as frequently as you can, just because they're there, and it's a good idea to get some stuff done while it's sort of fresh on your mind. If you let it wait too long, it gets a little more foggy back there, in the recesses of your mind. So please, I would say, go on and get as much done as you can. Get something done on all of them as you can, and but technically a week, but since you have three tests, that's probably going to be pretty hard to do. So whenever you can get them to me, but I would prioritize probably Cal 3, linear algebra, and then this one, because of the length of the next chapter, next test material. Does that answer your question, Jesus? Was that an adequate answer? Well, can't hear you. I hope. Can someone hear me okay? Anyone? Well, okay, you can? I heard a little something. Okay, good. All right, great. Okay, now where we left off last time, we had just finished. Okay, is this one more coming in? Let me see. Yes, Jemanuel is here. Or he's in the waiting room anyway. So, good deal. My first class was 100% attendance. Excellent. This class is 100% attendance. Excellent. My middle class was 6 out of 8, so 3/4 of the students were there, missing 2. So glad y'all are here. Good attendance today. Wish the other 2 would have been there, middle class. Okay. Javanuel, there was a question being asked before you came in. When are the tests due? And 3 of you have 3 classes under me, and it just happened to be all 3 of you had tests distributed last week. All 3 classes had them, and you are in 2 of the classes, so both of yours you got tests last week, and then Ryan is just in this one class, and he got a test for this week, last week too. So I was answering Jesus's question of when are they due. Technically, they're all due within about a week, but I always give you more time if you need it. And with 2 or 3 tests, you probably will need it. I would say prioritizing. I would say probably go with Cal 3 first, because we've already almost finished 1 out of 5 sections we're doing in that. I can't remember about linear algebra, how far we are. But it seems like chapter 2 is sort of a longer chapter than chapter 1 was, so I would say go for that one next. This is a long chapter, so you've got a little bit more time before the next test, so whatever that's worth, there it is. So where we left off for today was in 2.1.2, and we're going to talk about another class, not of differential equations. Now, this isn't anything that's competing with what we said before. It's just a very special kind of differential equation. They're first order, that's the same, but these are called autonomous first order differential equations. And we talked about this a little bit in section 1.1. We divided the class of ordinary differential equations into 2 types, linear and nonlinear. Now we'll consider briefly another classification of ordinary differential equations, the classification that is of a particular importance in a qualitative investigation of a differential equation, less so maybe in quantitative, but in qualitative it is. An ordinary differential equation in which there it is, in which the independent variable does not appear explicitly is said to be autonomous. Okay? So if the symbol X denotes the independent variable, then an autonomous first order differential equation can be written as f of y and y prime is equal to 0. Okay? Or in its normal form, that would be has y and y prime. Notice there's no x dependence here. Neither here. dy dx is equal to, and this is the normal expression, f of y. Only a function of y. No dependence on the independent variable. F is a function of, y is a function of x, but f, the function, what the differential equation gives you, the right-hand side, is not a function of x. We shall assume throughout that the function f in this equation here and its derivative f prime are continuous functions of y on some interval I. Remember, we always deal with the intervals. Okay? So here would be a couple of examples. dy dx is equal to 1 plus y squared. There's your function, only a function of y, no x dependence at all. This one would not be autonomous. dy dx is equal to 0.2 xy. That's a function of x and y. So this one's not autonomous, this one is autonomous. Okay? That's the only difference. Many differential equations encountered in applications or equations that are models of physical laws that do not change over time are autonomous. If time is your independent variable, these models of physical laws don't change over time. so they would only be dependent on the dependent variable. Okay, so we've already seen in 1.3 in an applied context, symbols other than x and y's are routinely used to represent dependent and independent variables. For instance, if t represents time, then here were some of the ones we saw. The change of an amount per change of time was only dependent on the amount, not on the time. This was true of your population studies. This is true of radioactive decay or radioactive, whatever the reverse term of decay would be, you know, things blowing up, you know, getting bigger. Okay. This was one that we used for your disease. Remember, that was a disease one. The rate of contagion or affection of a disease per unit time had nothing to do with time over here. All depended on what the number of infections were. Okay, that was our autonomous differential equation. This was Newton's law of heating and cooling. The temperature is the dependent variable, the time is the independent variable. The change of temperature per change of time had only to do with the change with the time. With the temperature, not with the time. Okay, and here was another one. This was the mixture problem is what they called it, where the amount of a material, salt or whatever you happen to have in a vat at any one time was related to the inflow and the outflow of that material. Nothing to do with time in the right hand side, only with the amount, the independent variable. Okay, now in every one of these examples, your K's here are your proportionality constants, and over here they actually gave you a proportionality constant because we worked out a problem with that one. The T sub m was your ambient temperature, okay, or they called it the temperature of the medium. Okay, the N was how many your original population was, if that was the disease example. Those are just constants. The independent variable in every case was time. No time occurs on the right hand side. The dependent variable, A here, X here, temperature here, and A here, those all show up on the right hand side. Each equation was time independent. Indeed, all the first order differential equations introduced in section 1.3 were time independent, and so every one of those was autonomous. I don't remember them all now, but they are saying it, so I believe it. Now, something we can do with that, and this uses the same terminology we used in calculus 1, I believe it was, critical points. The zeros of a function f in that original equation up here, I think it's already gone off screen now, and it probably will stay off screen. Yeah, this equation right here. dy dx is some function of y alone. The zeros for that function would then only depend on y. Okay, they would be a special point. We say that the real number c is a critical point of the autonomous differential equation 2, this one right up here, if it is a zero of f. In other words, f of c is equal to 0. Now, when we're dealing with critical points in Cal 1, that was usually of your independent variable. Okay, that was the C, critical points there. Since these are autonomous equations that don't depend on the independent, the C is the y values that give you zeros. Okay, still a critical point. It's also called an equilibrium point or a stationary point. So all three terms in this context mean the same. Back in the other, critical point would probably be the only one you would use when you were depending on the independent variable. Okay, excuse me just a second. Oh man, I left my glass of water in the bathroom, I think. Hold on. crammed down lunch with probably not drinking enough, so I'm a little on the dry side. Okay. So, okay. Now observe that if we substitute the constant function y is equal to c into that equation up here, okay, then both sides of the equation are 0, because if y is equal to c, dy dx is equal to 0. And that means f of y is equal to 0. So that's why we call it a critical point. Same as before, but then in Cal 1, it was the x. When x made it equal to 0, that was the critical point. Made that first derivative equal to 0. Now it's the y value. This means if c is a critical point of that equation up there that we've gone off screen now, then y equals c is a constant solution of the autonomous differential equation. Y is equal to c is a constant solution. Okay. Now, that constant solution, y of x equals c of 2, is also called an equilibrium solution, and the equilibria are the only constant solutions of equation 2. As already mentioned, we can tell a non-constant solution y is equal to y of x. You could talk about increasing or decreasing, determined by the algebraic sign of the derivative of dy dx. In this case, we do by identifying the intervals on which the x on the y-axis, because now we're dealing with the y-axis, not x-axis, over which the f of y is positive or negative. The function is positive or negative. So here's example 3. Here's a differential equation. dp dt is equal to p times a minus b times p. A, parenthetically, parentheses, a minus bp, close parentheses. Okay. Now, a and b, they're going to take both as positive constants. Both of them have to be positive here. Okay. Now, certainly when p is equal to 0, your f is 0. So that's going to be one equilibrium solution, or critical value. The second is when a minus bp is equal to 0. And I can't write on this screen, but I think that's an easy enough. Let me get this phone out of the way here. Let's see if I can find my pen here. I guess I will go down and do this. So let's go to the whiteboard. This isn't much to put on the whiteboard. But remember that equation that we're dealing with here is, by the way, I didn't tell you, flip over to page 40 if you did start here. Here's the equation. Now y'all have to tell me if this is showing up on your thing, because I have a big sort of yellow box around it. I can't see if you can see through that or not. Tell me. dp dt, p is the independent dependent variable, t is the independent variable, but the derivative depends only on the dependent variable, p times a minus bp. Okay. Now, if you're looking for places where that derivative is equal to 0, that obviously is going to be where p is equal to 0. That would be one solution. Or where a minus bp is equal to 0. What we can do there is add bp to both sides and get a is equal to bp and divide both sides by b. Now remember, we're assuming a and b are both positive. It's a pretty ugly b there, isn't it? So this would be where p is equal to a over b. So that would be another critical value for this problem. And that's why they said that in the book, that where p is equal to 0 and p is equal to a over b are your critical points. Now, can y'all read that okay? I know it's inside this. In mine, I have this yellow box around it, and it says, please move this window away from the shared application, and yet it's now it just faded out. Could you read it before it faded out? Yes or no? Can you read it now? Someone tell me something. Can anyone see what I've written on the board, on the whiteboard? Okay, good. Okay. I thought you could. Sometimes when it's a small box like that, people can't read what's in it, but the bigger ones usually they can, but I just wanted to make sure y'all could read it. Okay, so let's go back to the book. That's where they got this. Either P is equal to 0 or P is equal to A over B are your critical points. Okay. So the equilibrium solutions are P of t is equal to 0 and P of t. Remember, P is a function of t. Your F is just not a function of t. So P of t is equal to A over B. And by putting the critical points on a vertical line, the y-axis here, remember those are values for y, then you can identify something. So P equals 0 is a critical point, so that's going to be an equilibrium solution, and P is equal to A over B. But they told us that A and B were both positive, so you know that's above 0 here. Now, you divide this vertical axis into three parts. The part above A over B, the part in between 0 and A over B, and the part below 0. Okay? Now, they put some arrows in here, and I can't see any justification for why they put the directions they did. I think they're just giving you representative values. Okay? Now, this table came out rather squirrely in your book. This is supposed to say interval. I don't know why it got all screwed up in the letters. This should say sine of f of p, and this one says it fine. P of t, that's fine, and this is supposed to say the arrow. Okay, now, I'm sorry. Okay. I'm trying to see if there's any reason. I think they just gave you representative things. Okay. Above A over B, they're saying this function is always going negative. Okay. It's got to be monotonic. It can't be changing directions on you. Otherwise, it'd be another critical value. So this is monotonic, and they're just saying, let's just assume it's decreasing here. Let's also assume it's increasing between 0 and A over B, and that it's decreasing below 0. Now that's a good assumption to make. There's nothing about the problem that tells you it has to be that way, but it just says you've divided the p-axis into three regions. The one above A over B, between 0 and A over B, and below 0. Okay? Now, within each of those regions, the function can only be moving in one direction, either increasing or decreasing. They just picked some values. Okay? And I was trying to see if there's any special reason for them. Now, certainly, if P was positive, which would be anything above 0, then I don't know. There's just not a lot you can say about it. So anyway, we'll just assume those directions as they give them to us. Okay? Now, this expression here, this drawing here, is called a one-dimensional phase portrait, or simply a phase portrait. quite often I'll say a phase diagram, but I guess portrait is the better word. This doesn't seem very technical to me. Okay. Of the differential equation, dp dt is equal to p times a minus bp. The vertical line is called the phase line. The p-axis is called the phase line. Okay. Now, you can have solution curves somewhere in that region. Now, they're going to kind of leave this one alone and make up a new one down here. They're not very clear about this, and I found this part of the book a little confusing to read because they sort of jump from this problem just all of a sudden to something completely different. Okay, so understand that. We're kind of leaving that one alone for now. I think we'll come back to it, but we're going to leave it alone now. Okay, now they're going to talk about another issue, solution curves. Without solving an autonomous differential equation, we can usually say a great deal about its solution curves. Since the function f, okay, is independent of the variable x, we may consider f defined for minus infinity to positive infinity on x, or for some interval I on the y-axis. I think we skipped something there. Or for x, I'm sorry, between 0 and infinity, or whatever. You just pick an interval of x. Also, since f and derivative f of x are continuous functions of y on some interval of the y-axis, so notice they don't give this the normal name I is reserved for the y-axis. The fundamental results of theorem 121 hold for some horizontal strip or region R in the xy plane corresponding to the I. The I is on the y-axis, the interval on the y-axis. And so through any point x0, y0 in that region R, there passes only one solution curve of 2 of that equation. And here is the example of it. If this is your interval, I think I went down just a little too far. Okay, the interval I for y is from this negative value down here up to this positive value here. That's the only interval on which it's defined. Then if you have a point xy, x0, y0, a given point, some value x and some value y here, then there is only one solution curve that passes through that point. Okay, and it can be passing going downhill, uphill, or whatever. Now, I'm going to throw this in here. They're going to do it next. If this value up here, the upper limit of that thing, happened to turn out being a critical value, which a lot of times it is, then this is going to go up, but it's got to start bending over so it goes horizontal here. This one looks like it's already heading out here to become probably horizontal somewhere down, or near horizontal here. It won't ever be exactly, because the appearance of this says there's only one curve. It can't back up on itself, so it's going to be monotonically decreasing here between this value and this value down here. Okay, now let's go back to something like we just saw before, whether we have 3 regions. Okay, here's a critical value, C1. Here's another critical value, C2. Now in the last example, that was y is equal to p. I'm sorry, p is equal to 0. It wasn't a y-axis, it was a p-axis. P is equal to 0 or p is equal to a over b. So we're going back to that sort of concept, but not the same thing. So here's one critical value up here. It's a positive one, C2. The second one down here, C1, is also positive. And if you know that this curve is going south here, every curve will be going south here. In other words, decreasing. It can't change. Now this one obviously is going to go approach this C1 and get closer and closer, but never reach it. Okay? Up here, this has got some bending to do before it gets to C2, because it should not be able to cross C2, because that's an equilibrium value. Okay, so it's got to be monotonically decreasing there. And that's what these three regions show. The function is doing one thing here, could be doing the same or a different thing here, same or a different thing there. Okay? These are called your horizontal subregions. And since you picked a point in this one, that's the subregion you're in. Okay. Now they do a lot of blah blah blahing here. I'm trying to see if any of the rest of it is of great importance here. Let me say this. If this was your initial condition, at y at x equals 0 is equal to x0, y0, x0, y0 is on that thing, then you don't know beans about what's happening up here. The function, as far as you know, doesn't even enter R3, or if it does, you're not concerned with it. Same thing for R2. If you're here, this gives you information about where it goes from that view, from that point again. Okay, excuse me. My head is clogging up. Okay. Now, that's kind of what I'm trying to say here. By continuity of f, we must have either the f of y is greater than 0 or less than 0 for all x's in a subregion R sub I. In other words, f of y cannot change signs in a subregion. Okay? So, remember what f of y is? It's the derivative. It's not the function here, it's the derivative of a function. Because at one point you would say, wait, y can be negative down here. Yes, y can be negative, y of x can be negative, but f of y cannot. So this is obviously, an f of y is decreasing here, is negative here. It's going to be negative throughout that region R2. So that's why I said this has to stop going up here and start leveling off and approaching that equilibrium position. So it's got a big bunch of turning it's got to do real quickly. This one's already on its way to turning down here, so that can go on forever. This has actually got to bend pretty quickly to stay within that region and still be decreasing. So that's what I was trying to say. Let's see what's, okay, page down will not work here. Okay, so let me scroll down. Moving on to page 41. Still referring to the previous. Since dy dx is equal to f of y of x is either positive or negative in a subregion, the solution y of x is strictly monotonic. Now that's what I've been saying all along. I'm just ahead of the book here. That is, y of x is either increasing or decreasing in the subregion. It cannot change. Therefore, y of x cannot be oscillatory, nor can it have relative extrema, max or mins. Okay, it's got to be. Now, the y of x is bounded above by the critical point C1, as we saw before. So let me see if I can get that back down here again. Okay. It's on a different page, so it's going to be hard to get into the same thing. Okay, I think I might be able to do it. Okay, I'm going to stop right there. Nah, we're not quite going to be able to see it. So basically what it's saying, if you're within this region R2, if you're within that, in other words, your initial condition puts you in R2, then the upper bound that y can take on here has got to be C2. It can approach C2 but never touch it or reach it. then it has to come down here quickly and then gradually go to C3 or C1 down here. That's going to be its what it's, as y is, as x is increasing, y is decreasing towards C1, and it will never exactly equal C1. Where it equals C1, that is that solution that is that line y is equal to C1, or up here y is equal to C2. Those are those equilibrium positions that always satisfy. Okay, so if y is bounded above by a critical point C1, that would be down here in this region R1. Yeah, then the graph of y of x must approach the graph of the equilibrium solution, that's y is equal to C1, is either x goes to positive infinity or negative infinity. Doesn't have to on both cases, but one or the other. If y of x is bounded, that is bounded above or and below by two consecutive critical points, like C2 or R2 was here, in between those two critical points, here, then you're stuck in between there. You won't ever get out above or below. Okay? So it seems like they're almost saying the same thing over and over and over again, but I guess it is important. Okay. Now, with the foregoing facts in mind, let's examine the differential equation in example 3. Okay. Okay. All right. Sorry. I'm going to have to take a quick break here and go get my water. I've been drinking this soda, but it's way too sweet. I can't handle that. So I'm going to pause the recording just a moment here so I left my water. I don't know why I did in the restroom. I'll be right to drink. Okay. So what we're looking at in example 3 before, that's what I said, they jumped and sort of they introduced example 3 here, and then they jumped and started talking about a situation that was here that was very different from 3, and then they talked about this one, which looks sort of similar but not the same values. Okay, and now we go back to 3 again. Okay, so that's why I said this is a little squirrely. It seemed like they could have used the same example throughout, but they didn't. So the 3 intervals determined on the p-axis, or the phase line that they were calling it, but that's not what they called it before. They called it a phase portrait. Okay, so phase line I like better. The 3 intervals determined by the critical points, p is equal to 0 and p is equal to a over b. Going back to what we had before, here's p is equal to 0 here, here's p is equal to a over b here. Remember, a and b were both positive, so a over b is positive. Now if b is less than a, this is a very small interval here. If a is greater than b, then it could be a good bit larger. It doesn't really matter, just so it has those values. Okay, now they also told us that the arrow was pointing down in region 3, up in region 2, and down in region 1. Remember, I said can't see why they chose those, but it's perfectly fine to just have a direction for them. Now, because there is no upper bound here for region 3, this can go up infinitely. Can ever come back down again, because that would mean there would be a critical value. There isn't. Okay, it's increasing to the left constantly. Another way to say that is constantly monotonically decreasing here. So this can go to positive infinity in that direction. Okay, but over here it has to be approaching a over b, that critical value. That's because it's decreasing everywhere in that region. Increasing here, which means it has to be approaching 0 when when your x or t or whatever, I guess it's a t here, the t is approaching negative infinity, and it's approaching b over a when t is approaching positive infinity. So you have one of those sort of sigmoid type curves here in there. Has to be strictly monotonically increasing, and it can't exceed either of the critical values. Down here, since it's decreasing, has to be approaching x equals 0 or t equals 0 when t is very, very negative. I'm sorry, p is equal to 0 when t is very, very negative, and then it can be going and will be going infinitely far south as t is going to positive infinity. Okay, so this is just one possible drawing of that curve. With the parameters they gave us, this will be it. The three intervals determined on the p-axis or the phase line by the critical points 0 and a over b now correspond to the, in the TP plane. T is your independent variable, p is your dependent variable. Remember, there is no t dependence, okay, of the function f, okay. To the three subregions defined, R1 is anything south of any negative values for p. R2 is when p is between 0 and a over b, and then the third one, R3, is defined by any value p greater than a over b. Okay. Now, this is good for all t's, negative infinity to positive infinity on the horizontal axis. Now they go back to phase portrait. The phase portrait in figure 217, the one this one right here, tells us that p of t is decreasing when in R1. P of t is decreasing in R1, increasing in R2, decreasing in R3. Okay? So, for p sub 0, that's when t is equal to 0, the value of this is less than 0. That would be down here. Now they have three p0s here. You couldn't have all these at the same time. Pick one, any one of them, but not all three. If your p0 is down here, you know the function is heading in that direction. If it's here, because of the direction, it has to be going in that direction. And if it's up here, the p function is going down here. Okay? I think that's all it's saying. Now, excuse me. Okay. In a subregion like this one, R1 here, where p is decreasing and unbounded below, we necessarily must have that p is approaching negative infinity as t is going to positive infinity. Do not interpret that last statement to mean that the p of t is approaching negative. What I just said, we could have p of t is approaching negative infinity as t is approaching some value, capital T, okay, where t greater than 0 is a finite number that depends on the initial condition, p of t is equal to p0. In other words, when t is equal to t0, p is equal to p0. So what that's saying, p of t could blow up in the finite time. Thinking graphically, it could have a vertical asymptote there. So just like this is sort of indicating here, this is going downhill pretty fast, and we know it can't turn and come back up. So if this continues to bend down, it would be fairly easy to assume there could be a vertical asymptote where t is equal to some value here, and this line is getting closer and closer to that, but never touching it. That would be a case where the function would blow up as t approached that value t prime. So it doesn't have to be going to infinity. I sort of suggested it was because I couldn't tell that was actually bending down, but it doesn't have to be. Okay. The graphs of the equilibrium solutions P of t is equal to A over B and P of t is equal to T0. That's these dotted lines here, okay, are shown in the figure as blue dashed lines. The solid graphs represent typical graphs of P of t, illustrating the three lines just discussed, and that's this one, that one, and that one. Now, in the subregion sorry, I'm having trouble breathing here. Let me try soda again. It's way too sweet, but the carbonation feels good. All right. Let me scroll this up. I'm going to lose my figure there, but I can't show you this next paragraph without it. Okay. Now, back in example 2 that we did last time, where you had, yeah, that was it. dy dx is equal to sine y. That's autonomous because it only depends on y, not x here, and has an infinite number of critical points at every n pi. When sine y is equal to 0, pi, 2 pi, 3 pi, 4 pi, negative pi, negative 2 pi, negative 3 pi, infinite number. Moreover, we know that because the solution y of x has to pass through this point, in other words, your initial condition was y at 0 is equal to negative 3/2, it's bounded above and below by 2 consecutive critical points. Okay? Notice that the y value here is negative 3/2. So the first critical point above that was your y is equal to 0, and the one below that was awfully close to that, y is equal to, well, no, not really close, but negative pi. Okay? So that means you had to be, since this was a value, your initial value, you're within that band, you might say, of 0 to minus pi. You had to be within that. You couldn't be up here anywhere or down here because your initial point was there, and you can't cross one of those critical values. Okay? And sine of y is negative when you're between minus pi and 0. Now, don't get these confused. Sine of y is increasing between minus pi and 0, but it's negative. Okay? So that means the slope, because remember that's what it was, dy dx is equal to sine y, so that means it has to be going downhill there. Okay. Now, that's talking back about example 2. Let's move ahead to example 5. Okay. Here's our autonomous equation. Dy dx is equal to 1 minus y squared. Autonomous because the right-hand side has no dependence on x at all. None. Okay? Now, it possesses only one critical point, y equal 1. That's the only place that this is going to be 0. So everywhere above y is equal to 1, it's going to be monotonically going one way. Below that is going to be the other. Well, guess what? For any y value, whatever the sign of this is, when you square it, it's going to be positive. So this is increasing above and also increasing below. Has to be. Okay? So the phase portrait of this one would be increasing above y is equal to 1 and increasing below y is equal to 1, because your first derivative is always positive. And your critical point is the line y is equal to 1. Okay? So it's an increasing function in both regions there. Goodness, my nose is itching like crazy. Now, what if you did have an initial condition that y of 0 is equal to y0, and this is a negative, something less than 1? So that means whatever you had up here, it's not even in the picture. You're down here somewhere. Okay? Okay. I've lost where I was there. Oh, here's the initial condition. Y at 0, when x is equal to 0, y is a number less than 1. Now, it could have been up here, it could have been here, it could have been there. That's where they chose it to be, -1. It could have been down here. Wherever it was here, okay, wherever it was here, it has to be an increasing function going through that. It has to be approaching your I'm going to call it a horizontal asymptote, but it's not quite the same meaning as what we had before. Because remember, before we said you could touch or cross a horizontal asymptote. This one you can't. So it is a horizontal asymptote, but not one you can touch or cross. Okay? Now, so the solution y of x is increasing, and it says unbounded. It looks like to me it's bounded by y is equal to 1. Oh, it's bounded. I misread that. I read down here. Bounded above by 1. So when y of x is approaching 1, as x is approaching positive infinity. So yeah, as x is going very positive, okay? And this one doesn't seem to allow you a vertical asymptote here. So this would be going this way. Y is approaching 1. Okay? That equilibrium position. Okay. Now, y of x equal 1 minus 1 over x plus c is a one parameter family of solutions for that differential equation right here. They said see problem 4 back in exercise at 2.2. No, that's coming up 2.2. We're not there yet. Okay. A given initial condition determines the value for c. And that's what it always has. When you get that initial condition, plug in the x, plug in the y, calculate what c is. For initial conditions, say y of 0 is equal to -1, which of course is going to be less than 1, that would be this one here. Has to be less than 1 here, because that's the initial value. And here they don't tell you why, but we'll see in a minute. Y at 0, okay, they're doing two completely different problems here. For this first initial condition, you're down here, okay? And if you were to plug that value in, that y of 0 would be -1, plug that in here. -1 is equal to 1 minus 1 over x plus c. So I'm going to go back to my whiteboard and do that calculation for you. If I can find what I did with my pen, my pad, and my book. Okay. They're kind of jumping all over the place on these examples. And one reason I'm having a little problem, I failed to turn my page. We're on the page 42 now, example 5. Okay. Now, the first thing they tell us here is y of 0. Here's, okay, let me get my, okay, I keep fingering the wrong screen or pinning the wrong screen. So let's go back to our whiteboard here. Now I'm going to erase this because we're through with it. And of course, Ryan, oh no, there it is. That's part of my problem here. Let me, okay, I'm going to clear the drawings here. Now, usually when I do this, in fact, I think I will do it. I'm going to move you guys back to the right. You can't see that, but I can. I'm going to move this toolbar to the top and as far to the right as I can go. And now I'm going to adjust my whiteboard as far left and up as I can. Okay, now let me start my problem here. Here's example 5. Let me write down from the beginning. Your autonomous equation is dy dx is equal to, they just will not do an equal sign well, y minus 1 squared. Okay, so you know y is equal to 1 has to be a horizontal asymptote. Now, maybe that's what they're calling it. That's your equilibrium position. That's your single critical point. Okay, now, here's what we're assuming from there. Well, first they tell us here is a solution to that differential equation. Y of x is equal to, that one did a lot better, 1 minus 1 over x plus c. Okay, one parameter because this is a first order differential equation. You only need one parameter. There it is in your denominator. Okay, now a given initial condition determines the value for c. So here's the first one they're going to give us. Okay, y at 0 is less than minus 1. Y of 0 is equal to minus 1. I read it wrong. Equal to minus 1. That happens to be less than 1, less than your critical value, so we're somewhere down below. Okay, now let's take this information here, plug it in here, find out what our c is. Okay, so y of 0 is minus 1 is equal to 1 minus 1 over c. Okay, so we're going to, okay, what I'm going to do is add 1 over c to both sides and add 1 to this side. So that's going to give us 1 over c is equal to 2, which implies that c is equal to 1/2. Okay, so there's what the c is. So let's write down this again. Y of x is equal to 1 minus 1 over x plus 1/2. Now from that, you know, you have a vertical asymptote that x cannot equal negative 1/2. Okay, so that gives you two pieces of information. Okay, let's just imagine that's our vertical axis. Okay, and let's just imagine this is your horizontal axis. Okay. Ooh, that's not very horizontal, is it? Okay, we'll live with it. Okay, y is equal to 1. Okay, let's just tick off a few points here. 1, 2, 3, and 4. Negative 1, negative 2. That wasn't quite where I wanted it. Negative 3. Damn, this thing, it just drives me nuts. Okay. And somewhere down here would be negative 4. Alright, and we found out here that x can't equal negative 1/2. Well, if this was a 1 here, a 2, I'm sorry, a minus 1, minus 2. Yuck, it did it again. Okay, excuse me a minute. Okay, sorry. All right. I've got to get my pen to show back up here. There it is. So minus 2. So negative 1/2 is going to be here. That's going to be supposedly a vertical asymptote. We know already that y is equal 1 is a horizontal asymptote. So if you're at the point y is equal 0, x equals 0, y is equal minus 1, you know you've got to be in here. The function must be going here and must be going there. Okay, so you see this one, by the nature of its solution, it's not going to go, x can't go infinitely in both directions. Here the domain of this function is negative 1/2 to positive infinity. Not 0 to negative positive infinity, negative 1/2 to positive infinity. Okay, now they go into a lot of gory detail and tell you that. Now, this function, by the way, has another wing of it up here. Just the function itself does something like that. Who cares? This is not part of your solution for this differential equation. That differential equation could be up there, but only with different initial conditions. For these initial conditions, forget about this. You're down here. You're stuck down here. There's your one and only one solution curve that you could have for it. Okay. Now, the next thing they do here, and they really do such a lousy job of it, they say, well, what if you had, now I think I'll change color here. What color would you like? Name a new color. Anybody? A yellow. Okay, give me another color. We got red, we got blue, we got purple, we got green, we got brown, we got dark red, we got a pink, we got say again, dark red? Is that what you said? Okay, dark red. All right. Same equation, same differential equation, autonomous differential equation, same solution. This time we're going to do a different initial condition. In this case, y of 0 is equal to 2, I believe it is. Okay. Well, that 2 is greater than 1. So you're up here. Well, that changes everything. You don't just say, oh, there's some curve up here. No, it changes everything. You first go back here and plug that in. Y is 2, so that's going to be 2 is equal to 1 minus 1 over c, because x was 0 here. Okay, do the same thing we did before, kinda. 1 over c is equal to, now this time we are adding 1 over c to this side, subtracting 2 from this side, a minus 1, and that means that c is equal to negative 1. Well, if c is negative 1, then you go back and put this in place. Y of x is equal to 1 minus 1 over x minus 1. That's your c is minus 1. Well, you knew already your horizontal asymptote was still the same. Now your vertical asymptote is y cannot equal 1. Okay, I probably should draw this on two different graphs, but it takes me so long to draw a graph. So here is your situation. You got a horizontal asymptote here, same as before. Now your vertical asymptote is over here. Your initial condition here, so this means you got to be approaching here and approaching there. So now you're in this portion up here. Whatever you had down here, which is a solution curve for that equation, it's not a solution curve for this differential equation. That is the one curve that would fit these conditions, that initial condition right there. So your initial condition affects everything. Affects the interval. The interval is now negative infinity to positive 1, but not counting positive 1, going up to but not including positive 1. So that's where you are. This leg of it down here, which is actually graphically a solution, it makes no difference because your initial condition's up there. It sets your domain and it sets exactly what curve you're dealing with. Okay, now let's go back to the text for just a moment. This will be probably the last thing we're going to be able to get done today, because 3:45 is 3 minutes away. So let's go back to the book here and see, these are the, now I've got to move y'all out of the way. James, you're in the way again. All right, there we go. All right, so let's scoot this down. There was that first solution when the y of 0 is minus 1. This portion of the curve, it changed your horizontal asymptote stayed the same. Vertical asymptote, because you had to plug that back into this solution right here, that changed your vertical asymptote to be x cannot equal negative 1/2, so that made it there. So now you're in a curve down here, but when you change your initial condition and made it equal to 2, that then, when you plug that into your solution here, you got x 1 minus 1 over x plus 1, I mean minus 1. Yeah, then that made x equal 1 your vertical asymptote. So this point here had to be in this quadrant up here, not in the one down here. Okay, so that's what we were being shown there. For some reason that jumped all over the place. Thought I would get this done. Okay, now next thing they introduce here, and where we have time, 1 minute, is attractors and repellers. So here was your critical value, and these are your phase portraits here. Okay, and this showed up here, this is coming down, this is going up. So basically, whichever you're doing, it's being attracted toward when your independent variable, whichever it is here, x or t or whatever, is increasing. This is increasing towards c, this is decreasing towards c. that would be a repeller. Critical point C is a repeller. I'm sorry, an attractor in A. It's attracting from the bottom, it's attracting from the top. It's approaching the equilibrium position. This one, however, since the arrow is pointing upward here and downward here, this would be repelling for things above C, repelling for things below C. Initial point being here, that's where you would be, it'd be repelling. Here, it's repelling from above, but it would be attracting from below. Okay? But they're not talking about that. They call that a semi-stable state. It's stable from below, unstable above. And this one would be another semi-stable state. It's repelling below, so that would be unstable, but attracting from below, above, that would be stable. So those two would be called semi-stable because they're going basically in the same direction, above and below. So one of them's attracting, one's repelling. That's semi-stable, this one and that one. This one's repelling because they're both going away. This one's attracting, attractor, because they're both coming toward it. So that's what we're talking about asymptotically. Whoa, it did it again. All right, sorry about this. It's where I'll leave my cursor. Okay, so that is what they're talking about here, being an attractor, a repeller, unstable if it's repelling in both directions, semi-stable if it's attracting in one direction but repelling in the other. Okay, I think we've run out of time. We did. So we'll begin next time with this phrase, this figure right here, autonomous differential equations and direction fields. So let me get my pencil and mark that here and erase where we were last time I taught this. Okay, homework exercises here. I'm going to mark my place in my book here, and we almost finished 2.1.2. So let me just scroll on down here to show them to you. You've already done 2.1.1, and that was also talking about direction fields. So in 2.1.2, they pick up, sorry about that, I went right past it. Here we go. 2.1.2. You can do 19, excuse me, I've got hiccups now. Any of the odds, 21 through 27, you see them right there. Then also do 29, that's at the top of this page. Okay. And let's see. Let me make sure you can do 21. That may be what we're about to touch next. No, I think you can do them. Okay, and 29. Stop there. The discussion problems generally are in the back of the book, so we will begin there. So next time we'll begin on page 43 and finish 2.1.2 and then get started in 2.2. Finally, we will start solving some differential equations. We'll hit our first technique. These are what we call qualitative solutions, where there's really not a solution, but you get an idea where it's going to be. That's qualitative. Beginning with 2.2, we'll actually be solving some differential equations. The first kind will be called separable equations. Those are really fun, and I think you'll really enjoy them. And finally, we'll be doing that. Any questions? Okay, I'm going to stop the sharing if there's no questions. And if there's no questions, I'll end the meeting. So anything before we leave? All right, take care. Ron, did you have something? I saw your light come on. All right, take care of yourself. As some of you heard in the last class, one of my students, your classmates, came down with COVID. Fortunately, he's not got a very serious case, it seems like, from it. He seems to be doing well. So watch it, folks. It's out there. So be careful. Be safe. Take care. We'll see you. Well, I'll see all but Ryan tomorrow. Okay. And Jermanuel. I'll see the rest of you tomorrow, and then I'll see all of you on Wednesday. Take care. Bye-bye.